Okay, thank you. So welcome to today's HAO colloquium. Today we're very happy to have Dr. Yoshihiro Tomikawa. Somehow I was thinking Tomikawa here. That's because at the lunch we're talking about the location of your institute. It's a similar name. Sorry.
Yeah.
So Yoshihiro received his PhD in geophysics from the University of Tokyo in 2003. Working on trapped waves in the edge region of stratosphere polar vortices. And he then worked at NiPR as a postdoc researcher, and then stayed on as a JSPS research fellow. And currently he's assistant professor at NiPR, and also I think during that time you were also a visiting professor at University of Toronto.
Oh yeah.
And his research interests include atmosphere waves, tropopause and stratopause dynamics, stratosphere sudden warming, transport and mixing in the middle atmosphere, and dehydration in the polar stratosphere, which he will speak more today, and also middle atmosphere response to energetic particle precipitation. Yoshihiro?
Yeah. Thank you for introduction. At first, I'd like to thank Henry to give me a chance to talk in this colloquium. And I'd like to thank everyone for coming to this colloquium. I'm Yoshihiro Tomikawa from National Institute of Polar Research, Japan. Today, I'll talk about the stratospheric water vapor over the Antarctic. Yep. This talk is composed of two parts. In the first half, I'll show some results of the balloon-borne observations of stratospheric water vapor performed at Syowa Station in 2013. And in the second half, I'll show the results of trajectory-based analysis of dehydration processes inside the Antarctic Polar Vortex. As you know, the water vapor is a very strong greenhouse gas. So the stratospheric water vapor change has the potential to affect the surface temperature. This figure shows the stratospheric water vapor trend in the northern hemisphere mid-latitude. These black solid lines show the balloon observations at Boulder. And other colors show the satellite observations. As you can see, the stratospheric water vapor increased from 1980 to 2000 by 1 ppmv. And after that, the stratospheric water vapor experienced a strong, sudden drop in 2000. And then recently, it is nearly constant or slightly recovered. The Solomon et al. 2010 examines computed the radiative forcing of the radiative forcing with and without the stratospheric water vapor change. This figure shows the temperature trend since 1980. Green line shows the observation, and the red line shows the simulated temperature trend obtained without the stratospheric water vapor change. And blue line shows the simulated temperature trend obtained with the stratospheric water vapor change. So this gray shaded region represents the effect of the stratospheric water vapor change. So this shows about 0.1 Kelvin warming due to the stratospheric water vapor increase during 1980 and 2000. This is corresponding to about 1/3 of the surface temperature warming during this period. However, Heglin et al. 2014 casted a doubt on the global representativeness of these satellite and balloon observations. So the stratospheric water vapor trend is still controversial. The stratospheric water vapor concentration is mostly controlled by the dehydration at the tropical tropopause layer and the methane oxidation in the stratosphere. However, in the Arctic and Antarctic polar vortex, additional dehydration occurs because the polar vortex is very cold. Often it is colder than the tropical tropopause. Especially the Antarctic polar vortex is much colder than the Arctic polar vortex. So the stratospheric water vapor in the Antarctic stratosphere has a potential to show different change from other latitudes. This diagram shows the relationship between Antarctic stratospheric water vapor and ozone depletion. Well, Antarctic stratospheric water vapor contribute to the formation of the polar stratospheric clouds. Roughly speaking, PSC has two types. Type 1 is liquid droplet, and type 2 is the ice particles. And of course, both types of the PSCs contribute to the ozone depletion, but only the type 2 PSC contributes to the dehydration through the sedimentation of ice particles. In addition, the falling ice particles usually evaporate again during its descent. So this process is called rehydration. These dehydration and rehydration processes change the Antarctic stratospheric water vapor. This is a very unique mechanism. Then the change of the Antarctic stratospheric water vapor can change the long wave radiation, which also changes the polar vortex through any thermodynamical processes together with the change of the short wave radiation due to the ozone depletion. So such a relationship is very interesting and unique to the Antarctic stratosphere. Then to summarize this introduction, the Antarctic stratospheric water vapor can change its concentration through a very unique mechanism in the Antarctic stratosphere. And also they can play some role on the ozone depletion. In spite of these interesting features of the Antarctic stratospheric water vapor, their long-term observations have never been performed, except for several campaign observations performed by, for example, by Folger. And also, satellite sensors cannot capture the abrupt change of the water vapor concentration across the tropopause because it changes by a few orders of magnitude. Yeah.
During PSC period, usually it's dark.
Mm-hmm.
It's polar winter.
Yeah.
So how can it play a role?
Sorry, it is short of my explanation. Well, ozone depletion is most dominant in September and October, so in the spring season. Oh. So this effect of the shortwave radiation occurs in the spring season, and also the effect of this dehydration occurs at first in June, July, August, but its effect remains until November and December. So this change of the long wave radiation can affect winter, spring, and perhaps in the early summer. Yeah. So then, in order to perform the long-term monitoring observations of Antarctic stratospheric water vapor, we proposed the balloon-borne observations of stratospheric water vapor over Antarctica. This is the primary purpose of this observation and this study. And the secondary purpose is to examine the Antarctic dehydration and rehydration mechanism. This is well studied in the previous studies, but as mentioned later, there are issues to be resolved. And also, we are interested in the fine vertical structure of the Antarctic tropopause region and its effect on the stratosphere-troposphere exchange. Then, Here, I'd like to introduce our Japanese Antarctic research expedition activity. Well, this is called JARE for short. And this JARE activity started in 1957 during the International Geophysical Year. And 2 years ago, I joined the 54th JARE as a member of the wintering party and performed. I wintered at this Syowa station. Syowa station is located on the coast of the Antarctic continent. Well, during this wintering, I performed the balloon observations for measuring the stratospheric water vapor and spent 1.5 years together with penguins. For this observation, we use the cryogenic frost point hygrometer. This is a hygrometer developed as a successor of NOAA's frost point hygrometer. And this hygrometer uses chilled mirror technique and cryogen to measure the water vapor concentration. Then one important feature is that the CFH can be easily operated by non-professional users. Thanks to that, I could perform this observation. Well, during 2013, we performed 3 observations in July, September, and November. And fortunately, all the balloons reached above the 28 kilometers. And for this analysis, we also used the coincident satellite observations performed by Aura MLS. The horizontal and the vertical resolutions of the MLS observations are shown here. And the coincident conditions are the time difference less than 12 hours and the distance from Syowa station less than 500 kilometers. Then 8 or 9 profiles satisfied these coincident conditions. Then these figures show the obtained water vapor mixing ratio in July, September, and November observations. At first, red and blue circles represents the water vapor mixing ratio obtained by the CFH observation during the balloon ascent and descent, respectively. And also, this black solid line shows the Aura MLS, coincident Aura MLS observations with the error bars shown by dashed line. At first, in this July observation, the CFH shows a very high water vapor concentration in the stratosphere. This is much higher than the Aura MLS. But in this observation, the Syowa station was covered by the thick clouds below about 3 kilometers. So when the balloon passed through this thick cloud, the water droplet adhered to the balloon, and it evaporates in the stratosphere, and it affects the water vapor concentration observation in the stratosphere. So this part is not reliable. But in September and November observation, the Syowa station is clear sky condition. So the CFH observations show a good agreement with the MLS observations. Then one typical feature of these observations is there was seen dehydrated layers in the stratosphere shown by these dashed boxes. Then, in order to examine the stratospheric condition during these observations, we show the time equivalent latitude sections of potential vorticity and its gradient on 3 isentropic surfaces. Well, maybe some of you are familiar with equivalent latitude. Well, equivalent latitude is defined by the potential vorticity contour whose area is equal to the area of any latitude circle. Then this latitude is called the equivalent latitude corresponding to the specified potential vorticity contour. By using this, we can judge whether the parcel is located outside or inside the polar vortex. Then in this figure, the colors show the potential vorticity gradient, and the edge of the polar vortex is defined as the largest potential vorticity gradient. So, for example, in this figure, this region is corresponding to the polar vortex edge. And then, in these figures, these red stars shows the location, shows the equivalent latitudes of Syowa station on each observation date. So, for example, in July observation, Syowa station is inside the polar vortex at all the isentropic surfaces. However, in November observation, the Syowa station is outside the polar vortex at all isentropic surfaces. But in September observation, around 20 kilometers, the Syowa station is inside the polar vortex, but around 30 kilometers, it is outside the polar vortex. And around 25 kilometers, it is located near the polar vortex edge. So the stratospheric condition is different between these three observations. Then, in order to examine the temperature and pressure histories of each air parcel, I performed 10-day backward trajectory calculations. Well, at first, we put 75 air parcels around the Syowa station at each pressure level. Five in latitude every 1 degree, and 5 in longitude every 3 degrees, and 3 in time every 6 hours. So then for each trajectory, we computed the minimum water vapor saturation mixing ratio using the temperature and pressure data on each trajectory. So as a result, we obtained 75 minimum water vapor saturation mixing ratio for each observation data. Then then we chose its median value as the representative value of the minimum saturation mixing ratio. Then we plotted the median and minimum water vapor saturation mixing ratio for each observation. Here, this green stars show the minimum saturation mixing ratio. Then looking at these figures, it is found that the minimum trajectory-based minimum saturation mixing ratio basically explains the water vapor concentration in the dehydrated layer, as shown here. And also, we found one interesting feature around 25 hectopascal in July observation. Here, the trajectory-based minimum saturation mixing ratio is much lower than the observed mixing ratio. It indicates that this air parcel experienced any rehydration nor supersaturation during its trajectory. And in September observations, as shown in my previous slide, above this height, the Syowa station is outside the polar vortex, and below, inside the polar vortex. And it is found that the dehydration occurred basically inside the polar vortex. So, Then, in order to confirm the robustness of trajectories, I computed two kinds of trajectories using three kinds of reanalysis data. As shown here, these 6 trajectories show nearly the same results. So it is found that there is a little dependence on the kind of the trajectory and reanalysis data. Then we also performed the comparison with the PSC observation performed by satellite. Well, at first, this left panel shows the latitude height sections of polar stratospheric clouds. This shaded region represents the polar stratospheric clouds. And the right panel shows the orbit of the satellite. And this red cross represents the location of Syowa station. So this figure clearly shows the existence of the polar stratospheric clouds around 15-kilometer altitude near the Syowa station. And looking at the radius on the data, the temperature around this height region is about 190 Kelvin. This temperature satisfies the condition of type 1 PSC. So this is probably the type 1 PSC. Usually, the type of the PSC is identified by these satellite observations, but this is the observation in daytime. So in the daytime, there are much higher noise from the sunlight. So the type of the PSC cannot be identified in this data set. But the temperature showed probably this is a type 1 PSC. And we also examined the trajectories corresponding to this height region. Then they showed that those air parcels experienced the final dehydration more than 4 days before. And as shown in the previous figures, the dehydrated layer was extended more wider region. So it means that this observed PSC did not contribute to the dehydration. And type 1 PSC cannot contribute to the dehydration is also consistent with the previous studies. So this is the conclusion of the first half of this talk, where we performed the balloon-borne. We started the balloon-borne hygrometer observation at Antarctic Syowa Station in 2013, and they showed a very different stratospheric conditions between these 3 observations. And basically, water vapor concentration inside the polar vortex can be mostly explained by the dehydration in the last 10 days. However, we found a signature of the dehydration or supersaturation in July observation around 25 hectopascal. And PSC was also observed near Syowa station, but it didn't contribute to the dehydration. Then this observation is the first step of this long-term monitoring observation. So from next year, we will start the long-term observations using the CFH sensor at Syowa station. And I hope that Syowa station is only one Antarctic station which can monitor the stratospheric water vapor. Then we move on to the second half of this talk. Here, based on the studies using the CFH shown so far, we started the trajectory-based analysis using the satellite data for the fall period of the Aura MLS. Well, this figure shows the vertical distributions of typical temperature in the Antarctic region from May through October. Each color shows different months. And this red lines shows the frost point temperature corresponding to each water vapor saturation mixing ratio from 1 to 8 ppmv. So this figure means that, for example, in July, shown by this blue line, the air parcel can be dehydrated to about 2 ppmv, around 30 hectopascal. So usually, outside the polar vortex or above the polar vortex, the stratospheric water vapor concentration is between 4 and 7 ppmv. So considering from this figure, from June through September, this temperature shows this temperature becomes smaller than the 4 ppmv line. So in these 4 months, the dehydration is expected to occur. So here we focus on these 4 months in the following analysis. And purpose of this study is to quantify the respective contributions of usual dehydration process and rehydration, supersaturation, or incomplete dehydration to the stratospheric water vapor over Antarctica. And here we use the satellite data and trajectory-based analysis. Then in the future, I'd like to link this study to the understanding of the future change and climate impact of Antarctic stratospheric water vapor. About the Aura MLS water vapor product, basically the same as the previous talk. Well, the delta X shows the, means the horizontal resolution across the orbit track. So it is about 3 kilometers. But horizontal resolution along the orbit track is about 300 kilometers. And the vertical resolution is about 2 or 3 kilometers. And precision accuracy like this. And we used at first June through September 2013. And the available data is about 600 profiles per day. Well, in a similar way as the previous one, at first I examined the stratospheric condition in 2013. Well, these figures show the potential vorticity gradient in the time equivalent latitude sections at 4 isentropic surfaces. And this black dot represents the location of the polar vortex edge. So it is found that the equivalent latitude region poleward of 70 degrees south is always inside the polar vortex from June through September. So in the following analysis, we focus on this equivalent latitude region. Then again, I computed the trajectories, 10-day trajectories for each MLS observation. Here, we put 31 air parcels aligned latitudinally every 0.1 degrees centered at each MLS tangential point. So, as mentioned earlier, the horizontal resolution across the orbit track is just a few kilometers. So we put the air parcel only along the orbit track. So these 31 points cover latitudinal range of the MLS horizontal resolution. Then again, the minimum water vapor saturation mixing ratio on each trajectory can be computed. And then its median value of 31 minimum SMRs was defined as a minimum SMR corresponding to the coincident MLS observation. Then at first, left top panel shows the number of data set used for the number of data sets satisfied this equivalent latitude condition for each day. So above 100 hectopascal, basically about 300 or more data were used for the calculation. And the right top panel shows the Aura MLS water vapor mixing ratio from obtained as an average of these 300 or more data. So it clearly showed the water vapor concentration decreased from 5 or 6 ppmv to about 2 ppmv from June through August. And in the left bottom panel, we showed the minimum saturation mixing ratio obtained by the trajectories. So if these two concentrations are the same, it means that the dehydration is mostly explained by the dehydration in the last 10 days. In order to show whether the dehydration occurred or not more quantitatively, we computed the ratio between these two concentrations. So if this value is a unity, it means the dehydration occurred. And if this value is smaller than a unity, the observed concentration is higher than the water vapor concentration expected by the trajectory analysis. So it suggests a possibility of rehydration or supersaturation. So in this figure, this region shows the value, shows the ratio close to a unity. So the dehydration basically occurred in this height and period. But in this region, the value is basically less than a unity. So it means that the observed concentration is higher than the expected concentration from the trajectories. And in addition, another interesting feature is a very small ratio, less than 0.8, is observed around mid-August. So what is that? Then, in order to check this mid-August, we made the figure with more contours in these two figures. So comparing these two figures, it is found that this small ratio is due to the small water vapor concentration computed by the trajectories. Yep. Then at first, in order to examine why the ratio tends to be smaller than unity, I examined the sensitivity of the ratio to the temperature and residence time. This is a figure shown in the previous slide. Then if we add 1 Kelvin to the reanalysis data, this ratio becomes like this. So basically, in this, in almost all the region, the ratio became close to a unity. And if the air parcel must experience 6 hours for the dehydration below any saturation mixing ratio, it changes the ratio like this. So this residence time also makes the ratio close to a unity. So on the other hand, the very low ratio observed in mid-August is still observed in both figures. So these features cannot be explained by the temperature difference or residence time. Yep.
If I follow the second, what was the 6 hours? What does that refer to?
Ah, okay. Well, in the previous calculation, I assumed the instant dehydration. So if the so in that calculation, the lowest saturation mixing ratio in each trajectory is assumed to be the water vapor concentration of that air parcel. But if the air parcel needs some time to dehydrate, the water vapor concentration must experience any saturation mixing ratio or smaller value for more than 6 hours. So based on this assumption, we computed the trajectory-based saturation mixing ratio again. Yeah. Okay. Then, in order to examine why such a mid-August small ratio appears, I checked the temperature, the minimum temperature at each pressure level on each day. Here, this figure shows the minimum temperature in time pressure sections from the ERA interim reanalysis data. So you can see the very low temperature in early August. So this right panel shows the corresponding saturation mixing ratio. So it is considered that the very small ratio observed in mid-August experienced this low saturation mixing ratio in early August. Then in order to validity of this temperature distribution, I also checked the Mera reanalysis data and Aura MLS temperature data. Yeah, these two figures are very similar. And MLS shows the cold bias compared to the reanalysis, but basically the lowest temperature appears in early August. So this small saturation mixing ratio is basically due to this low temperature in early August. Then why such a low temperature region appears? Well, these figures shows polar stellar projection maps of temperature at 50 hectopascal from August 1st to August 16th. And this red contours shows the area of 180 Kelvin or smaller. So in August 1st, such a low temperature region doesn't exist, but it appears in 4th August, and it is expanded and located near the South Pole, and it is maximized around 10th August. But after that, the probably zonal wave number 2 structure was developed, and this low temperature region disappeared. So such a low temperature region is probably appeared as a result of quiescent polar vortex and probably the radiative cooling in the polar vortex. But it must be examined in more detail. Then hereafter, I show the interannual variability of the water vapor concentration and the ratio between observation and trajectory. At first, these 9 figures show the MLS water vapor concentration from 2005 to 2013. You can clearly see the interannual variability. Interesting feature is, for example, in 2013 is a very special year, the most dehydrated year. On the other hand, 2006 and 2010 are the less dehydrated year. As shown in the first introduction, such a dehydration or stratospheric water vapor is closely related to the ozone depletion through the formation of the polar stratospheric cloud. So we checked the extent of the Antarctic ozone hole. Then, in 2006, the ozone hole showed the nearly largest size. However, in 2010, it showed nearly smallest size in these 9 years. And 2013 shows a medium size. So as long as looking at these features, I couldn't find any close relationship between the ozone hole and Antarctic dehydration. But it needs to be examined in more detail.
Can I ask a question? How
Yep.
do you define ozone hole? Is that size? So area or how
Yep.
much ozone was destroyed?
Yeah, here I looked at area, provided by NASA's homepage. And these figures show the ratio between minimum SMR, trajectory-based minimum SMR, and MLS H₂O. So in the previous figures, we focused on this part in 2013, but similar feature can be seen in many years. So I think this is a robust feature in the Antarctic stratosphere and Antarctic dehydration. And the relationship with the temperature is not yet examined, but probably by examining the relationship with the temperature and its internal variation, I can find any relationship, any reason why such a very low ratio appears. Then this is a conclusion of the second half of this talk. Well, the trajectory-based minimum saturation mixing ratio shows basically a smaller value than the MLS observations. And it may be related to the cold bias in the reanalysis or wet bias in the observation or effects of the residence time. But currently, it is difficult to distinguish them. And trajectory analysis predicted more dehydration in mid-August, but observation didn't show such a feature. Such a difference is induced by the very low temperature region observed in early August, but why such a difference appeared is not yet clear, and this is a topic of future work. Then, in the future work, we will perform the satellite match analysis, which was often used for the ozone depletion study. This is the current state of my study. That's all. Thank you for attention.
Questions for Yoshihiro?
So I have some basic questions. The time scales for for the dehydration and for rehydration. So you mentioned the 6 hours as, if I understood, that could be roughly a time scale for dehydration, which would be the formation of cloud droplets and their descent out of the air parcel. Where does the 10 days come from?
Well, at first, the time scale for the dehydration is probably about 1 or 2 days or so. In the previous studies, the water vapor start to be condensate, and then it constitutes the droplet, and it falls because of its own how to say yeah, its gravity fall. It takes usually 1 or 2 days in the past studies, and I'm not sure about the time scale for rehydration, but I imagine it's fast. It looks faster than the dehydration, but it is. I'm not sure. And about the time scale for the trajectories, 10 days is determined based on the how reliable the trajectory is in the lower stratosphere. Basically, in the previous studies, the longest scale of the isentropic or kinematic trajectory is at most 2 weeks. And as long as I know, probably we can rely on the trajectory deterministically for 10 days or so in the lower stratosphere. But it is shorter in the troposphere and middle and upper stratosphere.
And the process of rehydration, you referred to if I understood, the evaporation of the...
Yeah, evaporation, yeah.
I would wonder, I mean, if they've already left the stratosphere by falling out, wouldn't it be more just due to mixing of air parcels through turbulence and so on? I don't know if that time scale could occur on over a few days, either mixing in the vertical or horizontal, that you're mixing moisture air parcels in with the...
Yeah. Yeah, I'm not sure, but it's very helpful comment. Thank you.
I have a couple of comments on this one also. So you mentioned possibility for rehydration at 20 hectopascal. But actually that figure up there shows, I mean, at 20 hectopascal, you're really at the top of the dehydration region. So there's nothing that can rehydrate falling down from above. So that's probably an indication that it's more a supersaturation.
Yeah, I think so. Yeah.
And then the comparison, era interim to your measured water vapor, when you assume, when you stick that assumption in there, it has to be 6 hours at least. For me, that means, well, the short-term waves don't play a role. So that says something, if that's really the case, that says something about how the dehydration process works. So forget about the short-term waves, and it's really the average that matters. But if you take the other assumption now, then you say simply, oh, era interim may just have a mean bias. Did you look at a comparison of the Syowa sounding temperature compared to era interim?
Yeah.
That would tell you something about the bias.
As long as I checked the radio sound data at Syowa station, the difference from the era interim data is less than 1 Kelvin. So, but in the era interim data, such a radio sound data is assimilated. So probably comparing them is not so meaningful.
It still tells you something how good era interim is, even though it's assimilated. I mean, there's a lot more data going into the assimilation, not just the song.
Yeah. But in this region, well, yeah.
I understand that.
Probably after 2006, the GPS radio occultation data is also assimilated. So in that sense, probably so many available data exist. Then the small difference between the radio sound and the era interim probably shows a very small bias.
To get to that high altitude, the instruments with balloons, do you have to treat your balloon in a special way or use special balloons?
Basically, the answer is no. We performed just kerosene dipping, and probably we didn't perform any additional treatment. Yeah.
I have a question on the earlier part. The first part, you said you saw type type 1 PSCs, and you think it's not related to it's later, I think, after dehydration.
Mm-hmm.
Do you see type 2, like, during the dehydration period? Type 2?
No, it is not yet confirmed.
Oh, okay.
Yeah. It is also need to be performed together with the satellite match analysis. So by when we perform the satellite match analysis, at first we observe the air parcel at any point. Then we compute the trajectory from this point, backward or forward. Then this trajectory fortunately encounter any observation at any location. Then comparing these two observations, we can estimate the dehydration between this trajectory. So if it shows the signature of the dehydration, then we need to compare it with the PSC observation. So if the PSC is observed where the dehydration are expected to occur, probably it's a signature of the dehydration and it's related PSC formation.
So have you tried to see if Calypso has matches along your trajectories back to back?
Not yet.
We examine the cloud distribution around your location.
Yeah. Pardon? Yeah. This is a
horizontal cloud map.
horizontal. You mean the geostationary satellite image? I've never seen this.
That will show you where are the water vapors come from or come out.
It is okay in the troposphere, but it is difficult in the stratosphere.
So you said that one of the objectives of taking the balloon measurements was to look at fairly small scale structure around the tropopods, and you didn't really get into that. Is that another study or?
Yeah, another study. Yeah, in around the tropopods, the tropopause inversion layer was discovered about 12 or 13 years ago. It shows very high static stability just above the tropopause, and in the Antarctic, this TIA tropopause inversion layer becomes the strongest in the world in summer, but it disappears in winter. So, I'd like to know its formation and dissipation mechanism. It's one purpose of this study, this observation.
Questions? Let's thank Yoshihiro again. Thank you.